it's great to be here. Enjoy speaking to you. As Brandon may have mentioned, I've been talking, I think as far up as New Hampshire, all the way down to Charlotte and Asheville. When I'm talking about my New Horizons project, the reason why I'm doing that is because everybody paid my salary for the past 13, 14 years on that for the coolest job in the world. You guys deserve a give back, so that's why I'm doing that. But tonight I'm going to talk about my hobby. So, and there's a fine line between a hobby and a profession at times. My hobby of astronomy got me into my profession. I was building telescopes when I was a kid, and that got me into being an optical engineer and doing all the neat things I did. And then as I got older, I came back into the hobby more. So I'm going to talk about the science I do as a hobby. And the interesting thing is, when we went to Pluto, before we got to Pluto, we knew Pluto had a really neat atmosphere. The way we knew that is by looking at occultations, looking at when Pluto went in front of a star, what happened. Instead of the star just blinking out sharply, just winking out, it faded out. When it came back in, it would fade back in is not the right word, but brighten back up gradually. And I'm actually going to show you some plots of that. And amateurs were involved in that research. So before we got to Pluto, we knew there was going to be a neat atmosphere because amateurs and professionals collaborated to do that work. So this is work that amateurs mainly do. It's cool science. Those of you who have telescopes and like to observe can do this. Those of you who don't, it's neat science just to be aware of. Okay? So as always with me, questions are welcome. I love interruptions. I love going in different directions. If you guys are really interested in one thing, I'll go down that path and I'll talk for a while and we'll just shorten things up maybe you're not quite as interested in. Okay? Okay, so let's start this way. We go back to October at 2 in the morning, and it was a work night, and I had to go to work the next day. So if you were in my front yard in wonderful downtown Gamber, Maryland, you'd see this. If you were with me and looking at a specific star in the constellation Sculptor, which is really low, by the way, to the horizon, happened to be right over my neighbor's house. So I always have to tell them, I'm going to be looking right over your house, not in your windows. Okay, so this is an image I'm going to start in a second. It should run as a video. On the bottom is time. So this is 6 hours, 1 minute, 45 seconds, and then decimal seconds. So hundredths of a second. And I want you to pay attention to that star right there. Okay? And we'll hope it runs. Okay, so not much is happening. Whoop. So you can still barely see it, right? It's still barely there. And then you wait, and you wonder what's going to happen, how long it's going to be. This is a much longer than typical one, and we'll talk about what happens in a minute.
Weren't you lucky to happen to get that?
Yep, and it's back. So kind of a neat party trick, right? Making the star disappear. Oops, wrong button, Steve. Okay, so here's the agenda. Now that I primed the pump here a little bit. We're going to talk about what occultations are. We're going to talk about why we spend time and effort to go out with special timing equipment, which is the equipment on the table here. Happy to chat with people afterward about what I have there and all. Why do we do it? Some example results, and I'll probably very briefly go through the basics of data collection, and maybe afterward, those that are interested, we can get together and talk about that in more detail. So we'll concentrate more on the science because it's more of a general interest. Okay, so what are occultations, and what do you do nowadays? You go on Wiki and you look it up. So an occultation is any time one object goes in front of another and blocks the first object, so you can't see it. In astronomy, we further narrow it down to basically 3 different types. There's lunar, which is when the moon goes in front of something. If the moon goes in front of a star or a planet, you can get some science from that. Planetary, when a planet goes in front of something or a planetary satellite goes in front of something. And lastly, we have what I'm most interested in, asteroid occultations. So when a planet goes in front of a star and blinks the starlight out. Okay, so first is lunar occultations, when the moon goes in front of usually a star we're looking at. And back in the old days, prior to LRO, Lunar Reconnaissance Orbiter, and Kauga, or however they pronounce the Japanese mission, we didn't have real good information on the height of mountains on the moon, craters, mountains. So we didn't have great information on heights. So you could use on the edge of the moon when the star would blink out versus the center of the moon to measure, in effect, the height of the mountains around the edge of the moon. And as the moon does its little wobble around the orbit, you get slightly different mountain ranges, different times of the month when the stars would go behind it. So at first, up till, the late 90s or something like that, we were still using that data to measure the height of mountains on the moon. Now the primary purpose, or the scientific value of doing that, is to discover double stars. Because when the moon slices in front of a star, if you got two stars that are really, really close together, so your telescope can't resolve them, they only look like a single star, the moon still slices the first one off first, and then there may be a delay of a fraction of a second, and then the other part of the star goes away. So instead of seeing light just completely blink out, it'll blink to half bright or something like that, and then blink the second time all the way down. So you can discover double stars that have never been observed before. And the rough value, they say, is if you look at 100 stars blink behind the moon that aren't regularly looked at, you'll discover one new double star. And amateurs who do that, when they find their double stars, will publish results. So they'll publish in the Double Star Journal, hey, I discovered a new double star. If Brandon and I both observed the same one, he did from down here and I up from Maryland, we can actually measure the angle of the double star and know the distance between it and the angle it's rotated. And we'd have that in the paper, we do. So kind of cool science, but there are zillions of double stars, so it's not as exciting to me, but a lot of my friends are really into it and they do that regularly. Okay, so then there's planetary occultations. So why time that? Well, again, back before we had missions to Pluto and Saturn and stuff like that, you'd use it to measure the diameters of the planets and their satellites very precisely. Now, primarily, the thing it's used for is for looking at the atmospheres, like we did on Pluto. And for example, there's an occultation where the moon of Neptune, Triton, I think it's the big moon, is going to go in front of a star in a couple of months. And the scientists are very interested in having amateurs look at that data to see if Triton has an atmosphere, because it's a very similar body to Pluto. So that's what mainly that's used for. And these are kind of rare anyway. And lastly, there's the asteroid occultations. And this is what I mainly do. So we can measure the size and shape of asteroids that you can't resolve from Earth by having a number of amateurs who are different. If the path of an occultation is across the Earth, different people line up there can measure the size and shape. And I'll show you how that works in a minute. So just hold on for how that really works. Again, we also discover double stars and measure, we also can measure the angular diameter of stars, because even though stars are basically point sources, they actually do have a little size. You just can't resolve them from Earth with an Earth-based telescope for the most part. So you can actually measure the size of larger stars. For some centaurs and Kuiper belt objects, rings have been discovered around them. And until 10 years ago, your average planetary scientist would say, those type bodies are too small to have rings. Well, the first ones they found were by doing occultations. And they, oh my gosh, there's rings. That wasn't supposed to happen. And it's also just a neat party trick. My wife loves to watch these. My wife has zero interest in astronomy, but watching a star blink out and come back on, she just thinks cool. Okay, so amateurs mainly do this. This is an amateur sport. And why is that? Well, I should say there's one major exception. The professional astronomers are really interested in Kuiper belt object occultations for a number of reasons. And they'll do those often. But asteroids and Jupiter Trojan asteroids and all, typically it's all amateurs doing this work. And you do it because you don't need big equipment. You need a little bit of specialized equipment that isn't all that expensive. and you need a telescope. And most of us who are, observers have telescopes. So you have half your equipment already. A lot of us are also used to going mobile. So if we need to go to see when an asteroid gets occulted, where that path goes across the Earth, we can get in a car and go, because some of us go to star parties. We're used to throwing our gear in, throwing a tent in, and going somewhere. We're also scattered all over the world, all over the country. So if there's an asteroid path going over Atlanta, we know there's people down in Atlanta we can call up and ask them to observe for us. And it's also a really part-time activity. The most dedicated people sort of like myself, I might sign up to do 1 or maybe 2 a week. And of course, half of them get clouded out at least. So a professional's not going to fill his time with doing this. And even though we're amateurs, we publish data regularly. So yearly, at least, we publish, here's the amateur observations of asteroids and the size and shape of a bunch of new asteroids that were done over the past year. So we regularly get credit in papers, or publish our own papers. Okay, so size and shape determination. In fact, is the next slide? Yeah, let's go to this one first. So you can imagine there's a star way, way out to the left here. And here's an asteroid that's out in the main belt, so it's AU and a half to 2 or 3 AU from us, depending on where it is in the orbit. When that asteroid, you're sitting here in Kingsport, say position C here. When that asteroid comes between you and the star, if the asteroid's faint, the star's bright, the star's just going to blink out like you saw in there. If the asteroid's bright as the star, you'll see it just get fainter. So there's 2 different things you can see. You can see the star go away entirely, or you can just see it get fainter. So if you have observers, you have an observer here up in Edmonton, you have me in Maryland, you guys down here, somebody in Atlanta, and somebody down in New Orleans. We would see the guy up in Edmonton, well, the shadow didn't go over him. The star never blinked out. So he got what we call a negative. I'll have the star blink out, but the star's only going to blink out as the asteroid moves across for a short time for me. So he blocks the star for a short time. Down here, you guys had a longer one. It blocked it for a bit longer. And ditto for the guy down in Atlanta and the guy in New Orleans, he didn't get anything. So what can we do from that is you can now connect the dots. And you can say that I know what the asteroid sort of looks like, and I know what the shape of it is. So you've resolved milliarc seconds. So I always get my, how small a milliarc second is. It's one of these things like if you're in Kingsport and somebody's holding a diamond Roanoke or something like that, but don't quote me on that. It's really small angles that you can't normally resolve. You've done that with a little teeny tiny telescope. You've done better resolving power than Keck with its adaptive optics on top of Mauna Kea in Hawaii, So you can do really cool science with really simple systems. Okay, so you use the times when you have the star disappear and come back. The critical requirement is you have to have people observing all that, what we call the shadow, right, where the star was blinked out. They can occur anywhere on Earth at any time. They can occur at noon, but of course you can't see it at noon. It doesn't do you any good. Right now, the other way they determine the shape of asteroids is light curve analysis. So this is also another amateur sport where they look and see how bright and faint the asteroid goes as it spins around. That's really good. They can get a good size and all, but they can't tell, for example, if there's a protrusion, something sticking out the side of the asteroid versus something sticking in. And they also can't tell you the diameter. They can only tell you how much it's changing. So if it's a really dark colored asteroid, it's a charcoal colored asteroid, it may be a lot bigger. And if it's a real bright asteroid, it may be a lot smaller, and they can't tell you that. They can just sort of tell you what they think the shape might be. We can tell them not quite as good information of what the shape looks like, but we can tell them if something's sticking out, sticking in, and we can tell them exactly what the diameter is. So it's very complementary. Anybody questions yet? Sir?
Yeah, so with that timing,
that time doesn't really take into account any possible motion of the asteroid at the time that occultation is occurring, right? And so
Yeah, I'll show you one.
The light curve would be a way to kind of balance those out.
Yeah, and the asteroid's rotating around, but I'll show you something that's interesting. Actually, on this one, isn't that perfect timing? So here is the data from the video I showed you at the very beginning. So you can see how many, each one of these lines is a different observer. My line happens to be right at center, so I was perfectly positioned. So I'm number, what am I, 14 or 15? 14. So I saw it blink out here, and I saw it blink back on here. And then my friends who were, I don't know if this is north or south of me, I guess this is north of me, saw shorter times and shorter times. And people south of me were there. So you can see this is a real circular asteroid. But if you notice one thing, I observed from Maryland as number 14. Number 15 was almost on top of me. So a guy in Tucson did that. So he got a little bit different times than me. So you see he's got blink on here, I blinked on there, and I blinked off there and he blinked on there. So either one of us made a mistake, which is possible, or as it went across the country, that shadow is going across the country, the asteroid's rotating. So we might have seen a change just due to the rotation of the asteroid in the 5 or 10 minutes between Maryland and Tucson, or Tucson and Maryland. I forget which way it was going. But this is a really good example of how well we can measure a size. Not real exciting shape, though. It's pretty much circular. Now here's a more interesting one. So here's one they did a few years ago. You can see it's shaped like a wedge of an orange. Something else to point out on this one, if you notice the list of people who observed this one, Scott Degenhardt, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. He did about 15 of these. So what he did was, this was such a bright star that he made these little telescope systems he calls Mighty Minis. What he does is he goes out to Walmart and buys 35 millimeter binoculars, cuts them in half, and puts a camera on the one end of them, puts them on a cheap $15 camera tripod, and record the data that way. So he'll go down the highway, and this time he was in Oklahoma, and he went just down a highway in Oklahoma, and every, I don't know how many kilometers or miles, every few miles would just stop, set up one of these stations and start a recorder. Drive down the highway another few miles and put another one, all the way down this highway. And that's how he got that great data there.
So, question, who puts all that together in this graph then? If it's a lot of amateur astronomers, how does that get coordinated back together?
Oh, okay, so I'll take my data and I'll observe and I'll say, okay, I saw this star blink out at 6 a.m., 14 minutes, 5 seconds, point whatever, and then it blinked back on at this. We have a North American coordinator who takes all that data and processes it and turns it into these things. And then there's a person in Australia who does a quality check on us, so he would go back to this one and say, there's a discrepancy here. And he'd collect data from me, the original data from me, and original data from the gentleman in Tucson, and he'd check them both, and either it's real and there was a rotation, or one of us made a mistake and he'd fix it, or have us fix it.
And that's all through the IOTA, right?
Yeah. So here are just a couple more. So I don't give a false impression. If you look at this one and this one, there's a lot of people and we get really good resolution. More typical are ones like this, where there's 4 of us or so observing. And you still get a very good measurement of size. You can see it's really elliptical, but you don't get a really good shape determination. That's our typical data looks like that. When we throw the entire team on it, for example, this double asteroid we did out in California at one of our, we meet once a year to have an IOTA meeting. We had 50 some odd people involved in this one, and you can see we got this great shape of both asteroids. And these are asteroids that rotate about each other. And if you compare this to the Keck image they took in advance for us so we could try to determine the phase and know where to put people, this is much better. We also occasionally get a shout out from Sky and Telescope. And every 2 years, Sky and Telescope will publish one of our results. The last 2 times I was lucky enough to be listed on here, so I have my cord here. And both times they spelled my name wrong. And this time the guy who submitted it was so angry because he always spells my name correctly, and they change it to the incorrect spelling that he made him print a correction in the following month. But it's kind of neat to see your name in Sky and Telescope every once in a while for something like this. And Sky and Telescope is a big supporter of our work. They regularly will have articles and examples of our data and all. And that's really neat to see, I think. We also have unexpected discoveries, and this is the neatest thing, if you ask me. But this is purely luck. So it's all the work you do to get the regular data, and then every once in a while, you just get lucky. So here's one we got lucky. See if you can figure out what happened here. Okay, so this is a Jupiter Trojan asteroid. And in a couple of seconds, it's this star here, it's the only star you can see, blinks out. Okay, it's about 10 seconds, so about 50 on the second here, 51 it's going to come back. Okay, back. Great measurement, right? Now watch when this turns to 0, 0. Don't blink, just watch that. Okay, what do you guys think happened? Yeah, so we look at that data, and that this happened to be my data. I was lucky enough to be the one who got this. And as soon as I saw it, I knew exactly what it was. I knew it was a satellite we discovered. The history behind asteroid satellites is very interesting because they've been doing occultations since the early 1970s. And there were several examples in the mid-1970s where people saw a long occultation. I think the really good example was down in northern Mexico. So they had a really good measurement of what the asteroid looked like. But a whole bunch of guys in northern Texas, I shouldn't say a whole bunch, like 2 or 3 guys in northern Texas saw another short blink out. But this was before they video recorded. This is when people looked at eyepieces with a stopwatch. And they said, well, it's got to be a satellite of the asteroid, because the asteroid, otherwise the asteroid would be shaped like say a circle with a huge protuberance sticking up, right? Doesn't make any sense. Couldn't happen. So people like David Dunham, if you've heard of David Dunham, he's the person who invented basically the occultation science. I worked with him at APL until he retired. Said, this has got to be a satellite. Well, the scientists said, well, categorically, asteroids cannot have satellites. Just the physics does not support it. And then they flew by with a spacecraft, was it IRIS? And the camera showed a satellite, and suddenly the physics changed. And it was okay. Now, the sad thing to me is the guys who originally saw that back in the late 70s have never gotten credit. So, we don't have proof. We don't have video like this. Anyway, so I knew what it was, but we had to, since there was only my data that showed the second one, because the second one is so tiny, the other guys who got the data from this, wouldn't have seen it. That we had to go through all the hoops like, okay, what if an airplane had gone through your field of view? I had a friend who's a birder. I had to go ask him, what's the largest bird that would be flying in the dark at night? Could it cover a C-14 aperture? And he had fun with it. It was like the answer was no. We went through all things like that to prove, you can't prove it, but to say, hey, couldn't have been a bird, couldn't have been a plane, couldn't have been Superman, right? So anyway, we took that data, we showed it to the professional astronomers. They were very enthusiastic about it. We published a paper on it in a referee journal. And now the neat thing is, there's, I think, 3 of us who have gotten one of these where we've seen a satellite with an occultation. There's a $5,000 prize to the first one that's proven. But it has to be proven completely independently. So like, somebody just use Keck or Hubble or something that we have nothing to do with and say, hey, we found a satellite around this asteroid. So the scientist I work with, I keep saying, hey, you got a little Hubble time? You could look at this thing for me? I'll split it with you.
Question, how large can an asteroid be and still be called an asteroid?
Well, we have minor planets now, right? So we have Pluto, we have Ceres and all, and how large is Ceres? Is it like 500 kilometers or a little bit more than 500 kilometers? So it isn't the size of it, right, with these new rules, it's the shape of it. So it has to have been rounded by gravity is one of the critical things. Okay, just some more on this. So there are 5 of us who observed that Agamemnon, which was the name of the asteroid. We're all in the mid-Atlantic. We got really good measurement of the size of Agamemnon, probably the best we've ever had. So even that science was great. And we had basically a bulletproof cord that showed there was something else there. So here's what the data looks like if you plot it out. So here's the signal level, how bright that star looked. And then the asteroid went over it, and it basically went to 0, went back up, and then 10 seconds later, for about a few tenths of a second, it went away again. And then here's what Agamemnon looks like here. And then here's what we think the satellite looks like and where it was in its orbit around Agamemnon. And if it ever gets proven, we get to name or suggest the name for the satellite. And I forget what the Greek name for it is, but it's the word for head in Greek. Because Agamemnon, of course, didn't his wife cut his head off when he had an indiscretion during the Trojan War or something? I don't know. Somebody who knows mythology can tell me about that, but David Dunham's wife suggested that, and everybody who knows mythology said, oh, that's the perfect name. Okay, so we think it's about a 4-kilometer asteroid satellite. Could be as large as 10, could be as small as 1 or 2. And the size and distance wouldn't be resolved by Keck, because they have observed this asteroid with Keck and adaptive optics, so they wouldn't have seen it in that data. And if it is true, it's only the 2nd Jupiter Trojan ever known to have a satellite. And we published a paper in Planetary and Space Science a year and a half, 2 years ago now on this. Now the cool thing is, I'll do a quick diversion here, is if you guys pay attention to NASA missions, there were just 2 new missions selected, 2 discovery missions. One of them is called Lucy, that's going to go to the Trojan asteroids. And the instrument I built for New Horizons, LORRI, we're going to build one, and we're going to put that on Lucy, so I'm going to be working on a mission to go to the Trojan asteroids. Unfortunately, they're not going to go by Agamemnon, so again, I can't prove it. Okay, so here's another cool science one we had, purely accidentally, also in 2012. So 9 of us set up 14 stations to measure a main belt asteroid, Mnemosyne, probably butchering the pronunciation. We had people from Maryland, where I was, all the way to California watching this one. And 6 stations were successful, so we got a really good measurement of the size of the asteroid. A decent measurement of its shape, too. But we found out that the star, when it crossed, was a double star. So we ended up publishing the fact that it's a double star, and it was even more important than that. Here's how we knew it was a double star. So if you look at this one set of data, so here's how bright the star was, and before it went to 0, it went halfway down. You see that there? And stayed there for a few seconds. Then it went away, and then when it came back, it's a little harder to see on this side, but it went, well, say this went down 2/3. Here it went up to a third down, and then went up the rest of the way. So what happened was it's a double star. The asteroid came around and blocked the brighter one first, so we're just seeing the light of the second one, then blocked them both, and then unblocked the first one, and it went back up 2/3 of the way, and then unblocked them both. So it was a cool discovery at the time, but then we found out that this was an unusual star. This was a variable star of a special type that there were a couple of Russian authors who had wrote a paper on it theorizing it's a close double, and that's one of the reasons why it's a variable star. It's one star is affecting the other and making it brighter and dimmer. So we we exchanged email with the Russian authors, and they were very, very excited about this data. They thought it was very important to the papers they had published on this type of variable star before. And this just shows you what the geometry looks like. You know, here's the asteroid, and here's the two stars where they were laid out, and you know, one's brighter than the other. The other interesting thing with this one is I got data from this one, but I didn't see two steps. But I didn't see the star ever go completely away. So what happened was I only saw one of them get occulted, not both of them. So it just brushed by the one for me. And the last thing I'll say on this one is at the Virginia Association of Amateur of Astronomy Societies in October, they get all their astronomy clubs together once a year for a meeting. And they have professionals come in and give them talks. So I was at that. And one of the scientists there from one of the North Carolina colleges is an expert on this type of variable star. So I said, did you see our paper on this proof that this is a double star? And you know, I pulled it up on my cell phone for him, and he was looking at it, and he said, oh, this is really interesting, except the Russians are wrong. It's not that type of not that type of variable star. So apparently there's a disagreement. The Russians think this is great data, and this guy thinks it's interesting, but it's not, doesn't apply to the real problem. Yeah, so here's the Russian paper on it, and like I said, we published our own paper on it. And here's another cool one that amateurs were involved with, and it's another one where the scientists initially thought this can't happen. So the Centaur Charlico, is that how you pronounce that? They were doing an occultation of this back in, I think this was like 2013, I'm sorry, 2013. And it was being occulted down in South America. So this is, you know, a Centaur, so it's out in the region of Neptune, so it's a distant asteroid. And they wanted to see how big it is, so they did the measurement. And what they saw was, they measured the asteroid, and that's really good, but they saw a dip, another big dip, and then on the other side they saw a dip and another big dip. So they discovered a ring around it, or two rings around it. The scientists thought there's no way a body that small could have rings. So, and again, this was professionals and amateurs, but amateurs made some of these observations. And the cool thing is I think some people made observations where they didn't get this because they didn't go over the asteroid, but the ring's a lot bigger and it went across the ring. So they just got double dips on each side and scratched their head for a while until they looked at the other data. And then of course there's the Pluto stuff. And again, amateurs have been involved with that. And you can see rather than a sharp edge when it would go behind the planet, it fades out as it goes through the atmosphere. Then you get no light and then it comes back on gradually. So amateurs have been doing Pluto data like this for years. And it's been very important to know about the atmosphere. Okay, so that's most of what I was going to talk about on the science. I'll talk a little bit about how we take data. I won't spend a lot of time on that because not everybody's going to be as interested on that. But does anybody have questions on the science we're doing? Okay. So I'll just go quickly through how we do our observations. First of all, before you make an observation, you have to predict it, right? Otherwise, you're just going to be looking at a random star and waiting 400 years for it to randomly blink out. So we go to a lot of effort to predict these things. We have software that some of our members have written to predict it. You can predict it yourself, and you can also have it that other people predict it for you, and there's just a web tool that tells you when this is going to happen for you. And then we use a web tool to recruit people across the path, so we get a lot of people who are able to observe for us. That's one of the reasons why I'm talking to you. I'm hoping to sucker a few people in to help us. And the web tool basically gives you a list of here's everything. In fact, I did this specifically for Johnson City. You know, here's a list of the coming ones for Johnson City. So the hard part I found, and I didn't realize this because this is something I'm just lucky enough to be pretty good at, is the hard part for people is to get on the right star field, to point their telescope in the right direction. If you have a really good go-to telescope, the ones that are computerized and point at the right direction, you're probably okay. But there's a lot of people who don't have good go-tos or have Dobsonians that they push around the sky to get to the right spot. And it's not like going to a deep sky object. It's not like going to Ring Nebula where when it's in the field, it's obvious. You see a ring, you see a nebula, you see a planet. This is just stars, just dots. And a lot of people just have a real hard time learning to look for these mini asterisms, these little triangles of a certain shape that tell you, oh, that one's here, and there should be another bright star there if I'm on the right field, and do that. And I didn't realize that for the longest time, that this is what a lot of people are intimidated by. And there's also time pressure, because you have to be there at the right time. So if you have a really good mount, that's a good idea, but practicing really helps. So typically you need an 8-inch telescope to do reasonable number of these, but you can do a lot of work with smaller telescopes. You try to time when the star disappears, when it reappears. You use GPS timing equipment, which is what I have over there. It sounds intimidating, but it's really not. It's just the numbers on the bottom we inject into the video. We print those on each video frame with the little box in there. So, you know, most people who are interested in observing, if you're more just a science person, you might not be interested in observing, that's fine. We'll already have a telescope. So you have most of your investment already. Go-to mounts, I think, are easier, but you can use anything. You can use a push-to mount. You can push to a star that is ahead in right ascension, at the right same declination, and point there and wait for the star you want to see occulted go right through your field at the right time. It's called pre-points. Hardware, I won't go through this list in detail, but it's probably of order a few $100s worth of hardware you need if you want to be a diehard and really do it like I do it. And I put my portable stuff in a box, so all my stuff's together and I can just plug it into the camera and I'm ready to go. We have all sorts of software to predict, to do with the analysis and all. That's all free. That's really sophisticated software that our guys have written. And we have a guy up in Rochester, New York, who collects the data for us and puts it together and turns it into those shadow maps that we use. And then that data gets published. And the software does the graphing like this, so you can measure exactly when the time is. You can see there's times written on here, and you can just click on the software and it'll tell you what time it was exactly. And then there's a report form, so you have to go into Excel and file a report. And it goes up to Rochester and gets turned into that great data you see. Now, what I've also run into is there's a lot of people who've tried this in the past, because David Dunham used to do like I do, and he would go from club to club trying to convince people to try this. And people would try it, and they would observe, and the asteroid would never blink out. This would just happen. They do it a few times, and they say, this isn't any fun. I'm not doing it anymore. That's because we weren't doing a good job of predicting. There's this new satellite, fairly new satellite, that the Europeans put up called Gaia that measures where the stars are unbelievably precisely. And it's also measuring where the asteroids go. That's going to improve our ability to measure, to predict when these happen to an insane degree. So in a few years, it's already starting, but say 3 years from now, if I say it's going to happen in downtown Johnson City, it's going to be within 6 blocks in either direction of where it's going to be. Where right now, I'll say, Johnson City, but it could be Kingsport, right? So anyway, it's going to get a lot better. So positives about it, it's amateurs doing real science, real important science. The professionals ask us to do this. It's a team sport. You have friends doing it. And when your friends are doing it, you know you're doing it, you signed up for it at 2 in the morning and it's a work night, you're going to get up and do it because you don't want to let your buddies down. So it gets me out using my observatory a lot more. We have a lot of freeware available. The negatives, though, the things that kill you, is it's even worse than regular astronomy for weather. Because it isn't, I'm going out and taking a pretty picture of Ring Nebula and I can wait a half hour if I have to. No, it has to be perfectly clear in that direction right at this time or you're doomed. And I went down to a club in southern Maryland during the holidays, and we used their club observatory and one of their members' observatories, perfectly clear prediction The northern observatory got clouded out with 5 minutes to go when there was supposed to be no clouds, and the one I was at, the southern one, we got clouded out with 90 seconds to go. So that was just a heartbreaker. And also, you know, yeah, this is a few $100s, but a few $100s is substantial. I'm not going to say it isn't. So there is the cost of the hardware. Now, there are other uses for a video system if you buy it. A lot of people are using them to record with a wide-angle view when meteors come down. And if you get several of these, you can predict where the meteor could have landed if it made it through the atmosphere. People are also using it to look at the dark area of the moon, looking for lunar meteor impacts, little flashes on the moon. That's kind of cool to do. And I'm not kidding, but the biggest user of our timing boxes are the UFO people. We sell more boxes, that's fine. And we have a group called IOTA, International Occultation Timing Association. So we publish a journal, we have a Yahoo group, we have the software, we do books. We have an online manual, 450-page online manual you can get for free. And we do have a $25 a year membership fee, but other than getting the journal, you don't need to be a member to participate. You can do everything else without being a member. And we're not just asteroids, we also do lunar occultations and lunar grays, where a star will just go along the very edge of the moon and it'll blink in and out a whole bunch of times. Not good science anymore, but really cool to see. There's an Astronomical League observing program. I forget, is your club an Astronomical League club?
Yes.
So you can get one of the what I call the merit badges for occultation timing, along with a whole bunch of other things. And I'm actually the guy who runs that, by the way. So I went through and I looked, here's your next opportunities if you're actually interested in doing this. There's a 73% one that goes through Colonial Heights. It also comes up here. In fact, I'll show you, just look at the map. Here's the map. So just south of Kingsport is the center line here, and we're predicting the shadow goes from a little bit above Bristol to a little bit south of Johnson City. And then there's one at the end of the month. This is probably the best one in the eastern US, or one of the best ones this year. This is a very bright star. An 8th magnitude star is actually very bright in the sport. And there's a 91% chance that Colonial Heights will be in the shadow. If you go up to Bristol, you'll get a 99% chance. It is a really bright star. So this is something, if you have a little spotting scope or something, if you point to the right spot of the sky, you can just watch this by eye and see this. So there's the path of this one. So see, it's coming up from the Greensboro area, and it's going in this direction. So it covers, you know, all the way from Johnson City almost up to Wytheville. And like I said, it's not often you get an 8th magnitude star that happens to. And then there's another medium probability one at the beginning of February. Sort of runs the same path. And then there's a whole bunch of websites we operate. Unfortunately, we're an old club, so everybody was doing individual things when we started. So there's a whole bunch of different websites. You know, like Joe Blow runs this one, and another guy runs that one, and they all sort of overlap a bit. We don't just have one unified one. And we have our 450-page book, and I'm happy to help anybody who ever wants to try this. So I think that's all I have. Questions?
So, I mean, obviously a video camera makes all this work a lot easier, but do they still take information if you're doing it? You know,
Yeah.
just stop
Yeah, we do.
or-
Yeah, and in fact, I don't know if you paid attention, but a couple of years ago, Regulus was going to get occulted. So Regulus is one of the brightest stars in the sky, right? It's a first magnitude or so star. The path went right over New York City. So they were spinning people up in New York City to see how many people they could possibly have observed this, because you don't need a telescope. You just need to sit there with a stopwatch. And we went one step further. We made an app, an Android app, and I think there was also an Apple one, that you just hit the button, and you got your data, and then you just hit another button, and it would submit the data. And of course, the entire path, including Bermuda, which one of our members last minute flew to Bermuda, imagine how much that cost, and everybody, the entire path all the way up to northern Canada was clouded out.
Well, you still got to go to Bermuda.
Well, David is the type of guy who will fly down there, and it's like, I got to come back for the so-and-so occultation, so he was there for like a day. Any other questions?
Well, did you ever see any UFOs on so-called streets or something you can't explain?
In fact, I was up in Roanoke, and one of the guys up there is interested. I stayed at his house last night, and I was showing him one of the videos I took. And in the video, at the end of it, suddenly there's this object that goes across, nice and slow like that. It's a satellite, and I would think about 1 out of 5 videos I take, you see a satellite go through your field. It's amazing how many there are up there. When I was a kid, seeing a satellite was something special. Now it's like, get out of my field of view. Anybody else? Yeah.
What's the typical field of view when using your camera with your telescope?
Well, on my C14, these are little chip cameras. In fact, you come up here and look afterwards. So they're half-inch CCDs, are like that. The half-inch, of course, does not mean half-inch literally. So my field of view on my C14s of order are 12 arc minutes across. So it's hard to point. Smaller telescopes, of course, are going to have larger fields of view. They're just coming out with a cooled deep sky camera with a chip about this big that has GPS built into it. So you can do timing with that. So if you're looking for an all-in-one camera to photograph DSOs, and photograph planets, and also do this, QHI has that camera. It just came out. I have one on order. I haven't gotten it yet. Anybody else?
Who's paying for the $5,000 reward?
The people who put up the money have chosen not to be identified. I have a hint of who it is. I think I know at least who some of the people are, because some of the guys who are into this hobby, they fly all over the world. I think they have money, none of my business. And if I get the $5,000, I'll say thank you to everybody, and that'll be it.
Why is it just 5,000 if you've got all these rich?
I'd rather have 5,000 than nothing.
So these are all known asteroids. It seems like, it might be kind of difficult, but with today's computer capabilities, is anybody just looking at a patch of the sky, looking for occultations that are occurring to find?
There are people talking about doing that. I don't think that amateurs have started doing that yet. There's some professional small observatories, I think, are doing stuff similar to that, but they're doing it for all sorts of different reasons, not just asteroid occultations. But there's what we really need after this better prediction I was telling you about that's really going to help. The next thing we need after that is a much faster camera, because then we're going to get into, okay, we can now see these tiny asteroids, these 1 kilometer asteroids, or near-Earth asteroids that go across the sky so fast. In order to time them, you need something that goes faster than a video camera's 30 times a second. You need something that goes 300 times a second. So that'll be the next thing we'll be looking for. And actually, that QHI camera has the ability to go real fast. Anybody else? So anyway, like I said, if you're ever interested in trying this, I'm happy to help you any way I can.